Hello everyone. In this video I'm going to talk about NanoVDB and how I've taken advantage of it for use with Axiom, my sparse GPU accelerated fluid solver. I'll also do a mini tutorial in the end to show how to use it with the OpenCL SOP in Houdini 18.5, just in case you want to create NanoVDB tools for yourself. So really quickly, NanoVDB, for those of you who haven't heard about it yet, is a library developed by Nvidia that lets you work with VDB data in a way that's compatible with a device such as a GPU. It works with CUDA and OpenCL, and the code is open source just like OpenVDB, making it very easy to pick up. You can read all about it on Nvidia's website linked below. The current catch is that NanoVDB's structure is read-only. You can't add or remove data from it. But because sampling the tree is so much faster, it's a perfect fit for something like a GPU render engine that needs to ray-march through a volume. In my case, it would not make much sense to use it as a compute grid for Axiom. I can't modify the grid, and needing to constantly convert back and forth between NanoVDB and OpenVDB would take way too much time. It would be much better used for something like sourcing, and you'll now find a NanoVDB option under the solver's input settings in 18.5 only. It's on by default, and the nice thing is you don't need to change the way you work. You can give the solver VDB sources just like before, and it will take care of the rest. So to walk through what we have here, I created a squab, converted it to a VDB, just density for now. Then I'm just duplicating it, renaming it as temperature, and merging them both together so we have temperature and density. Then over here, I have a box for our collision object. Turn that into just a SDF VDB surface. Merge together our two sources and plug them into two solvers. One solver here is using NanoVDB, and the other one is not. So I just moved over the one that's not using NanoVDB over to here, and I'm merging over the two to get the result. So if I go ahead and run the performance monitor and play back, we can pretty clearly see how much time is actually being spent in this particular situation just on sourcing. Yeah, it's pretty definitive just how crazy it is and how fast you can actually source things in sample VDBs on a GPU compared to doing it on a CPU. In this case, this is sampling VDBs on a 2080 Ti, and the one above it is being sampled on a 12-core 2nd-gen Threadripper. Cool, so now let's talk about the NanoVDB SOP inside of 18.5. So the first thing you're going to do is create an OpenCL SOP, like so, and want to create some things to actually work on. So I'm going to create a very simple grid. This is going to be a grid that we're going to be deforming here by a volume. And let's just get a whole bunch of points. And then I'm going to create a VDB. So I'm going to drop down a squab geometry. Get the easy one. Create a VDB from polygons. And I'm just going to create a very simple density field here. Then I'll create a transform node so we can kind of move it around in our scene. And then because our OpenCL SOP only has one input, I'm actually going to merge these two objects together so you have access to both of the data, even though we're only technically going to be modifying the grid itself. So if I drop down a merge node, and just combine that, and combine the volume and plug it in. Then here we're going to say we want to use code snippet, so we can actually write our code here. Then under bindings, we're going to actually take the data from the input and actually bind that over to OpenCL. So I'm going to first take the position of our grid by doing P. This is going to be an attribute coming from P as well. It's a point attribute, it's a float, and it's a size 3 because it's a vector position, X, Y, Z. We're going to create it readable and writable so we can also modify its position. Then I'll create a new parameter as well. I'll call this simply VDB. You can name it VDB density, VDB temperature if you have multiple fields, but for now we just have one, so I'll just keep it as VDB. And you'll see there's a new option down here under volume like we had before, but now you can use VDBs as well. So it's going to ask us what volume do we want, and I want to use our density volume. And you can also fetch other information, but we don't really care about that right now. The VDB object actually comes with most of this data built in, so we don't have to really worry about it when we're sampling it. Cool. So then I'm going to make sure we are doing the first writable attribute, which is our position. So we're going to iterate over all the points positions. Then under the kernel, I'm going to generate a kernel, just copy this text, and paste it in. you'll see it's just outputting the grid in the volume, but it's not doing anything now. It's just kind of set everything up for us. So just confirm that's working. I'm actually just going to move all the points up, just like you would do with like a vector angle. But I'm just going to do an OpenCL just to make sure that everything is working. So here, I'm going to take our position, this float key that we have, and we're going to open the brackets to access the array. And what we're going to do is we're going to say the index that we're being given here, idx times 3, because this is a vector type kind of array. This is storing x, y, and t positions. So for every single index, we want to look 3 kind of indices forward as far as this one single 1D array is concerned. And then I'm going to move them up, so I'm going to add 1 to it to get the y position. And I'll just say plus equal, let's just do 2. And you'll see everything moved up too, so everything seems to be working. So now let's move the points up based on the value of the volume that it's currently sampling. So for every single point position, we're going to sample the VDB value and then kind of move the point up and y based on how what the value of that VDB sample is at that position. So to do that, we first need to create a VDB grid data object. But to access that, we actually need to include a few extra files. The first one that we need to import is called NanoVDB. And we're also going to fetch another one while we're doing this. And that is called CVDB util. And so CNanoVDB is a library that actually comes when you download the source code of NanoVDB. But CVDB utils is a few utility function that SideFX actually gives us access to when we're creating our own NanoVDB type tools. So this includes a few things that make it a bit easier than just using the like the raw source code that comes with NanoVDB. So you can see we have our VDB object, just casts the global void, and we actually want to cast this to a CNanoVDB grid data object pointer. So here what I'm going to do is I'm going to declare it const. It's going to be a global CNanoVDB grid data. It's going to be a pointer. We'll just call it grid. And we're going to have this equal our VDB object. And before we assign it, we're actually going to cast this to the exact same thing. So I'm just going to copy and paste this guy here. Like so. Make sure we don't get any errors, and we did. What's the problem? I probably misspelled something along the way. CNanoVDB grid data. VDB. What's it complaining about? Oh, I misspelled global. Global. And global. There we go. Cool. Next thing we're going to need is a read accessor. So this is a type of object that actually lets us fetch data from our grid and actually work on it and like sample indices and sample the volume itself. If you want to do something like a trilinear interpolation, you do that using the grid's accessor. So to create that, again, we're going to call it CNanoVDB underscore read accessor. And I'll call it ACC. That. And I probably spelled it wrong again. Yep, read accessor. Very complex names, but it's okay. So before we do anything moving forward, we're actually going to see if what kind of type our field is. Is it a vector? Is it a float? We only care about it if it's a float in this case. So I'm going to do an if statement. And inside of here, I'm going to do CNanoVDB grid data valid f, and we're going to give it our grid. And so now, if this grid object that we created is a valid float field, that's what the f is for, and I spelled that right, valid, yep. if it's a valid float field, we're actually going to do something. So I'm actually going to copy and paste our move up code and put it in here now. Like that. And you can see it is a valid grid because everything's still moved up 2 units. So next, we're actually going to associate our accessor with our grid, and we're going to do that using a function called NanoVDB get read accessor, and we're going to give it our grid and our accessor. Get read accessor. Oh, I forgot to give it the reference. There we go. So now we're actually going to do a sample. So the first thing we need to do is get the position of our point and put that into a float3 object. And I'm just going to create a float3 sample position. Dot x is going to equal the x position of our p. And I'll just copy and paste this code to save a bit of time. And we're not going to get the y, we're going to get 0 to get the x position. And I'll copy and paste this line for the y and z position as well. There we go. So next we're actually going to get the value of our volume at this position. So we'll declare a value float and have that equal C NanoVDB sample f function. And inside we need to give it our grid, we need to give it a reference to our accessor and our sample position. Like so. So now, instead of adding 2, let's add the value of the volume of the position. And you'll see we have a few little bumps. So if I go ahead and scale up this volume, you'll see that all the points inside the volume actually get moved up by the value that is sampled. So if I were to do something like a VDB combine and actually increase the value of that, you'll see it gets stronger as the value of the VDB increases or decreases, or goes negative. And one little quirk of this is because all our data is combined, of course it's going to output the VDB itself on the output. So if you don't want that, you can just go ahead and blast this away. Just say, I don't want density. And now I'll get just the grid out there. Cool, so that was a very simple introduction to how NanoVDB works with the OpenCL solver in Houdini 18.5. So that's it. The new build of the solver is now out, so feel free to pick it up or upgrade to it if you're an existing user.